Hello guys, welcome back to your favorite and India's most affordable learning platform, Physics Wala. So in today's session we are going to start a new chapter, so that is the mechanical properties of solids. Okay, so and after this we will start the fluids chapter and surface tension. Okay, so this chapter is going to be very easy, and you are going to get short questions and simple questions in your competitive examinations. Okay, so I recommend all the students to practice more questions from these chapters, because this is the easiest one where you can score easily by doing the simple questions, simple logics. Okay, chalo. So today we are going to start the lecture number 1 of this chapter. I am going to allot 3 lectures for this chapter. So today the first lecture where we are going to discuss, so what is the elasticity, what is stress, strain and Hooke's law, and what is the modulus of elasticity. So especially we'll discuss some questions related to the Young's modulus of elasticity. Okay, clear guys? Chalo. So as usual, I just need your attention for the next 1 hour. Just be with me, avoid all the disturbances around you guys, and at the end of the lecture it's very important to prepare your own short notes. And one more thing, when you're coming to the next lecture, just revise your short notes. Okay, so whatever the chapters that we have done till now, you should have your own short notes for that. You might, like, you can get the short notes or mind maps from web, anywhere. Lot of mind maps are there, but I'm telling you, so the short notes that you prepare is worth 100 times than any better publications short notes or mind map. That's for sure. Any publication, even it is PW mind map or PW short notes prepared by some other faculty of PW, it's worthless when it's worthless than your notes compared to your own short notes for you, because your short notes, it's prepared by you guys. Actually it's prepared by you so that you can easily understand, okay, so this formula we can use this in these questions. You will get idea easily. Okay, clear? So that's why always prepare your own short notes. Okay, chalo. So let's get into the topic. So first let's see the basics. So what is elasticity? So the deforming force and the elasticity. So a force that changes or tends to change the shape or size or both of an object. So if you apply any force on an object, so it might change the shape of the object or size of the object, or both shape and size. So that force is called the deforming force, so which causes some permanent change in the object, size or shape or both. Okay, so the elasticity is a term, so which means it's a property of a body or material to regain its original configuration after removal of the deforming force. So if you apply some force, so let's suppose take the sponge, so now you apply some force, so now after you remove the force, so the deforming force, so the sponge will come back to its original position again. Yes or no? So that's called the elasticity. Yes or no? So up to its elastic limit, so up to where the body can regain its original configuration, so up to elastic limit. Once the elastic limit has crossed, so the body will not regain its original configuration or original shape or dimensions. Clear? Chalo. So this is deforming force and this is elasticity. So the elasticity is measured by actually the modulus of elasticity. There is a term called the modulus of elasticity. The modulus of elasticity. The modulus of elasticity. So this modulus of elasticity, it's a measure of the elasticity. Okay, so which is more elastic? See here, steel or rubber? So the one which has more modulus of elasticity, so it is more elastic in nature. So here we are going to discuss the Young's modulus of elasticity in this today's session. So we can say that the Young's modulus of elasticity is greater for steel than the rubber. Okay, so that's why the steel can regain its original configuration easily than the rubber. So that's why, which is more elastic here? So the steel is more elastic than rubber. Steel is more elastic than rubber. Clear? Chalo. So this is the basic information. What is the deforming force? What is the elasticity? So the measure of elasticity is the modulus of elasticity. So that's it. Now let's go for the another term, that's called the stress. So what is the stress? So it's a internal restoring force per unit cross sectional area is called stress. So consider this is a rod of length some L. So now this is a cross sectional area A. Here we talk about the length and cross sectional area actually. So this is of some length L and its cross sectional area, let it be A. So now you are applying some force Fe. You are applying some force. So now this force develops so some restoring force this side. So up to the elastic limit, whatever the external force that you are applying, the restoring force also will be same as of the external force. So the restoring force also will be same as of the external force. So then we can write the stress formula as stress is equals to, so it's equals to, so the restoring force by the cross sectional area per unit cross sectional area. So per the cross sectional area. So in this up to elastic limit, so we can say that the restoring force is nothing but the deforming force. So here this Fe is a deforming force. Okay. So up to elastic limit, that deforming force will be equals to restoring force. So here the restoring force in this particular case, I'll write here. So in this particular case, the restoring force is equals to deforming force. So the restoring force is equals to, so the deforming force. Done? Yes. So now here I can write the stress is equals to restoring force by cross sectional area, or I can also write this as deforming force by cross sectional area. Deforming. So deforming force by the cross sectional area. So deforming force by the cross sectional area. So here see, I can write, so the stress, it is actually denoted by the sigma, which is equals to, so either restoring force Fe by A or the deforming force Fe by A or the restoring force. So the restoring force Re by A. Re is the restoring force I am considering. So or else you can write Fr better. The restoring force, right? So Fr, write it as Fr. Better. Yes. So Fr by, so the cross sectional area, both are same. Done. So this is a stress formula. So what is stress now? The force upon area. So now what are the units of stress? So the stress units, force units are Newton per, so the area meter square. So force per area. So Newton per meter square are the units of stress. Okay, clear? Remember this, guys. And I am giving you the homework. So that is, so what is its dimensional formula? So the homework, so write the dimensional formula. Write the dimensional formula of stress. Done? Chal, good. So next, so there are different types of stress. So I'll just stand here. Let's see this one. So the internal restoring force per unit cross sectional area is called stress. So one is a longitudinal stress, the other one is a shearing stress or the tangential stress. So the other one is a volumetric stress. So here the longitudinal stress, again we have two types. One is tensile stress, the other one is a compressive stress. Now, so if you take an wire or something material, so you apply the deforming force this side, we apply the deforming force this side. Okay, so across its cross sectional area. Then, so the restoring force will be developed in this direction, and then the restoring force will be developed in this direction. Okay, actually you are applying the tensile force, yes or no? So you are stretching this one, so then it causes the tensile stress. So this tensile stress formula is either Fe by A or Fr by A, Fe by A or Fr by A. So up to elastic limit, so the deforming force will be equals to restoring force. So then the body will gain its original configuration. Done. So the compressive stress means you are trying to compress the body. Okay, so here the deforming force inward, so here also the deforming force inward. So now where the restoring force will be? Restoring force will always act towards its original configuration, to regain its original configuration. So this side and this side. So here also the tensile stress, the compressive stress will be again the Fe deforming force per cross sectional area, and then so Fr per cross sectional area. Done. Done this part. Chalo. So here also the same formula. And then coming to the shearing stress or tangential stress. So if you apply the force tangentially like this, so the base is going to be constant, and then it will be tilted this way. So let's suppose this is the length, let the original length be L, this one, and then so it is shifted by some distance x. Okay, and then so it is tilted by some angle phi. So now we can write here, so this tan phi is equals to opposite by adjacent, which is x by L. So the tan phi is equals to x by L, we can write. Clear this part, everyone? Done with this? Sure. Next. So next the volumetric stress. Sorry, here tangential stress formula I did not write it. So this is the tangential force upon the area. So the tangential force upon area. Clear? Chal. Then, so the what is the volumetric stress? So what is the volumetric stress? See here. So initially, let's suppose, let me write. So the volumetric stress is equals to, so the force upon the area, right? Force upon the area. So shall I write the force upon area is also the pressure? The force upon area is also the pressure. Yes or no? So initially it's the original volume V. So now it is compressed by an volume delta V. So upon applying the force from all the directions, it's a 3D. Volumetric stress means you can simply imagine. So that has a 3D. Okay, so it's, we can say the perpendicular force upon area. The perpendicular force upon area. It's a perpendicular force upon area, which is also equals to pressure or the change in pressure, we can write. Okay, so the sigma volumetric stress is equals to the change in pressure, you can write. So, done. Clear this part? So just note this down. Done. Chalo. Let's move further. So let's take the question number 1. So what's the question says here? So read the question, guys. The ratio of radii of two wires of same materials is 2:1. If they are stretched by the same force, the ratio of their stress is. So let the wire A and the other one is a wire B. So now, so the wire A, so sigma A, the ratio of their stress we required. So sigma A by sigma B is equals to, so they are stretched by the same force. They both are stretched by the same force. Force upon the area of the first one A by the force of same force by area of the B. So force gets cancelled. Area of B by area of A. So I can write sigma A by sigma B is equals to B. So let this has a radius R2. So let it has a radius R1. Okay. So then what's the radius formula? So the pi R2 square by pi R1 square. Here cross sectional area means the circular cross sectional area for the wire we take. Then So pi gets cancelled. So the sigma A by sigma B is equals to R2 square by R1 square. So what is R2 by R1? So it's given. So we can write, so this is 2 by 1. So R2 is 1, R1 is 2 whole square. So which is nothing but, so 1 is to 4. Yes, so the correct option is 1 is to 4. See here, wire 1 to wire 2 is 2 by 1. So here R2 by R1 they wrote. So that's why 1 by 2 whole square. 1 is to 4 is the correct answer. Done? Chal, good. Next. So let's go for the question number 2. So there are two blocks of masses 2 kg and 3 kg are connected by a metal wire. So going over a smooth pulley as shown in the figure below. So the breaking stress of the metal is given 2.4 by pi into 10 to the power 9 Newton per meter square. So the minimum radius of the wire used if it is not to break. So the breaking stress is this much. Okay, so let's understand this question first. Here, so first let me find the tension. Let me find the tension. See, so some tension T and some tension T, and here this side 3G force will act, this side 2G force will act. So obviously it accelerates downward and it accelerates upward. So the basic pulley concept. Yes. So now I can say this is the basic Atwood mission. It is the basic Atwood mission. In this basic Atwood mission, can we find the tension formula? So what's the tension formula? We already know 2m1 m2 by m1 plus m2 into g. 2m1 m2 by m1 plus m2 into g. So simply substitute the values. 2 into, so what is the mass? 2. So other mass 3 by m1 plus m2. So which is nothing but this one m1 2 plus 3. So 2 plus 3 into g value they consider 10. So they gave it in the question. So now I can write, so 4 12 by 5 into, so 10. So I can write 2 times, so 24 newtons. So the tension is equals to 24 newtons. Fine. So now, so what is the minimum radius? The breaking stress is given. What is the breaking stress? Stress formula is what first? Force upon area, right? The stress is force upon area, right? So then here I am writing, so the stress sigma is equals to, so the force, what is the force? See, if the stress has to be maximum, right? So the force upon the area has to be minimum. We have to find the minimum radius. So the area will be minimum when the radius is minimum. The simple concept, right? So the maximum sigma, maximum stress is what? The breaking stress is a maximum stress. So this breaking stress means it is a maximum stress we can apply, so that this pulley cannot break, this string cannot break. So the maximum stress, in place of that I am writing 2.4 by pi into 10 to the power 9 is equals to, so what is the force that is acting? The force is nothing but the tension here, by pi into, so this area will be minimum. Pi is however constant, area will be minimum when, so the radius is minimum. Done. So that's it. So now you got the values, substitute here. So 2.4 by pi into 10 to the power 9 is equals to, in place of tension I am writing 24 by pi, so the r square minimum. So here pi gets cancelled. So then 2.4 1 time, 2.4 10 times. So then I can write, so here 110 cancel, 8 will be left. So I can write r square, the minimum radius, is equals to, so 1 by 10 to the power 8, which is nothing but 10 to the power minus 8 I can write. So then r minimum is equals to 10 to the power minus 4. R minimum is equals to 10 to the power minus 4 meters. So 10 to the power minus 4 meters, option 3 is the correct one. So basic calculations, that's it. Done. So let's move further. So now let's come to the next topic, that is strain. So strain is defined as the ratio of change in shape of an object to the original shape. So it's a change in configuration of an object by the original configuration of the object. So let's suppose if the change is taking place in terms of the length, consider. So let's suppose the change is taking place in terms of length. So then the strain is denoted by epsilon, which is equals to the change in length by the original length. The change in length by the original length. Okay. So if the change takes place in length, so the change can take place in any thing like length or area or volume. So it can be anything. Okay. So it will have no units. Why? See here. So numerator length and denominator also length. So that's why no units. So if it has no units, so then it's dimensionless quantity. Remember, the strain is a dimensionless quantity. So strain is a dimensionless quantity. Done? Chalo, good. So next, so there are again different types of strains. So the longitudinal strain, so when the change in length takes place, and then shearing strain, so when the tangential force is applied. So let's suppose it has moved by some distance x like this, so then it's a shearing strain. And then volumetric or bulk strain. So here the strain formula we can write it as, so the change in length by the original length. So the change in length by the original length. Let's suppose this is the original configuration, then you applied the force, so there is some change in length. So the change in length by original length is a longitudinal strain. And the shearing strain is nothing but, so originally it is like this, so it is changed by some x by, so the original length L, so which is also equals to tan phi we can write here. Okay, so tan phi is equals to x by L. So and then, so what is the volumetric strain? So which is the original volume, let it be V. So the final volume, so it is shrinked by some delta V, so which is nothing but minus of delta V by V is a volumetric strain. Volumetric strain. Clear, guys? So the volumetric strain part. So you can just simply take the magnitude of this. So consider, see, this is always occurs in the liquid, let's suppose. So if some force is applied from all the ends, that means some pressure is applied, F. So here F, F, F. So like that, if the force is applied, so then it will be shrinked. So then we can write this as, so the strain is equals to the magnitude of change in volume by, so original volume. So these are the different types of strains and different types of stress. So now we have understood what is strain and what is stress, and what are the types of stress and what are the types of strain, right? Chalo. So let's move further. So this longitudinal strain is possible only in solids, guys, always. So the longitudinal strain is possible only in solids. This is possible only in solids. Done? Chalo. So direct theory question, you should remember that. Then, so next, so we have got the question. So try to do this question. A wire of length 2.5 meters has a percentage strain 0.012% under a tensile force. So the extension produced in the wire will be, see here. So we have got the solution, let's see. So the strain is equals to delta L by L. We know this formula. So its original length is 2.5 meters. So what is the percentage strain? So 0.01 percentage. So I can write here. So this percentage is equals to, so delta L by L percentage. So now simply substitute the values. This one is given as 0.012 percentage is equals to, so this change in length we have to find. So the original length is 2.5. So now do the simple calculations, that's it. So only you have to do the calculations here, that's it. Do the calculation, simple thing, right? So what we can write? So the delta L by 2.5 is equals to, so this I can write as percentage, so which is 100. So that's it. So now the delta L will be equals to, so we need what is the extension produced? Extension produced means the change in length. So which is equals to 0.012 into 2.5 in by 100. So let's write this way. So the delta L is equals to, let me write 12 into, so this one 25. So here 10 to the power minus 3, here 10 to the power minus 1, which is 10 to the power minus 4 I am writing. So by, so 100, which is 10 square. So which I can write it as, so or else let's let this be 100 here itself. So 100 we will cancel. So 25 ones are 25 fours are 4 ones are 4 threes are. So which I can write it as delta L is equals to 3 into 10 to the power minus 4 meters. So the options are in mm. Okay, so what I will do is the delta L is equals to, so 110. So let's write 10 to the power minus 1 means, so 3 by 10 into 10 to the power minus 3 shall I write? So we can write this, right? So 3 by 10 is 0.3. So into 10 to the power minus 3 mm. So see here. So 10 to the power, in place of 10 to the power minus 3, I'll write mm. So the final answer will be 0.3 mm. Clear, guys? Chal. Good. Next. So let's take one more question. So if the angle of shear is 30 degrees for a cubical body and the change in length is 100 root 3 centimeters. So find the volume of cubical body. So try to solve this question on your own, everyone. Simple question. So simply, so the volumetric strain formula you can use. Sorry, now shearing strain. Shearing strain, simple formula, right? So we have already seen that when you apply the force, so this is the change. How much it is? 100 root 3. So this angle is how much? 30 degrees. So now the strain is equals to, so the tan phi is equals to, we have got x by L. So let's write, so this is a x by L. So this is a cubical body they are saying. So let's it length from each side be L. So then tan phi, so tan 30 degrees is equals to x. Let's find x. X is 100 root 3. So by find L value, that's it. So what is this one? So 100 root 3, tan 30 is 1 by root 3. So which is equals to 100 root 3 by L. So here, so I can write L is equals to 100 root 3 into root 3. So we have got, so 300. So L is equals to 300 centimeters it is. So now I need the answer in meter cube. So let's write L is equals to 3 meters. So but what I need actually not the length. So find the volume of the cubical body. So what will be the volume? So the volume is equals to simply L cube, right? The volume is equals to L cube. What is L? 3. So 3 whole cube. So which is nothing but, so 927, right? 27 meter cube. Simple basic calculations, that's it. Option 2 is the correct one, guys. Done, everyone? Chal. So let's move further. So try to solve this question on your own. So try to solve this question. A uniform cube is subjected to volume compression. So if each side is decreased by 1%, so then the bulk strain is. So they are asking us to find what is the bulk strain. So try to solve this question on your own. I'll give 2 minutes time. First, done. See here. So consider this is a cube initially. So initially let's its side be A. So the initial volume will become A cube. Now it is shrinked. So it is shrinked. So by how much? Each side is decreased by 1%. So now shall I write, so the final volume will be equals to, so the initial volume minus, so A cube by 100. It is decreased by 100%, so 1%. So shall I write like this? it is decreased by 1%. So that means A minus A by 100. Shall I write? A minus A by 100. Shall I write? Yes or no? So that's what, sorry, why I wrote A cube. So this is the new side A dash. 1% decreases means A minus A by 100, right? 1% decreases means. So what will be the new volume now? So A minus A by 100 whole cube. That's it. So now what they are asking, what is the bulk strain? So what is the bulk strain formula? So which is equals to, so the delta V by V, that's it. So what is the change in volume? So delta V is change in volume. So which is nothing but V initial minus V final. So what is V initial? A cube minus, so what is V final? So A minus A by 100 whole cube. A minus A by 100 whole cube. So now do the simple calculations. Do it fast. Do it on your own. Do the calculations on your own, guys. A cube minus A by 100 whole cube. So do the simple calculations, so you'll get the answer. First, done. Use the basic concepts. So shall I take, so let's do one thing. Let's take A cube out here before writing here. So let's take, so simple steps we follow. So 1 minus, so 1 by 100 whole to the power 3. So here A cube minus, so this is A cube into, so 1 minus, so 1 by 100 whole cube. So 1 minus 1 by 100 whole cube, right? So then which is equals to A cube minus A cube into, so see here, so shall I write here 1 minus, so 3 by 100 this part, 3 by 100. So why? So you have learned this in the binomial expansion. So 1 minus x to the power n is equals to, so 1 minus n into x, where x is n is far less than the x is far less than the 1. Yes, so the same concept I am applying here. So here A cube, so minus A cube into 1, A cube minus half minus plus, so here 3A cube by 100. So here A cube gets cancelled, it will be 3A cube by 100. So this is the change in volume. So we have got change in volume. Now we need the strain. So which is equals to, so this is 3A cube by 100 by A cube, so that the A cube gets cancelled, right? So it is 3 by 100. So which is nothing but 0.03. So the correct option is 0.03. Done. Clear, guys? Everyone? Chalo, good. So let's try this question, the question number 7. So let's try the question number 7. First, so a uniform sphere is compressed such that its radius decreases by 2%. So the volumetric strain is, what is the volumetric strain? See, we know that the volumetric strain delta V by V. Yes or no? So here, shall I write it decreases by 2%. So what a uniform sphere, so that means its radius decreases by 2%. So then only the total volume decreases by 2%. So I'll write simple this way. So the 4 by 3 pi r cube. Yes or no? So let's apply the concept. So delta V by V will become, so 3 into delta R by R. So delta V by V is equals to 3 into delta R by R. So here what is delta V by V? So the delta V by V we have to find, right? So the volumetric strain, yes. So is equals to 3 into, so what is the change in radius? So we have got 2%. So that is 2 by 100. So which is nothing but 3 into, 0.02. So which is 0.06 is the final answer, delta V by V. So which is 0.06. Option 4 is the correct one, guys. Done. Chal. Chalo. So let's go for the next concept, that is the Hooke's law. So what Hooke's law says is, for very small deformation, stress in a body is directly proportional to corresponding strain. So the stress versus strain curve up to the elastic limit, it will be directly proportional up to elastic limit. For very small deformation up to elastic limit, so the stress will be up to the elastic limit. So the stress is directly proportional to strain. So what is stress we have got here? The stress is sigma, so which is directly proportional to the strain. Yes or no? So or else let's write this way. So the stress, and then so put the proportional constant E into so the strain. So here we can write E is equals to, so stress by strain. Stress by strain. So this E is called the modulus of elasticity. So this E is called the modulus of elasticity. So E is called the modulus of elasticity. Okay, so where this E will have the same units as of the stress. So whatever the units of E are there, so same as of the stress, because the strain has no units. So what are the units now for the elastic modulus of elasticity? Newton per meter square. The same thing, Newton per meter square. Done. Understood this part, everyone? Chalo. Next. So according to Hooke's law, Hooke's law of elasticity, if stress is increased, so then the ratio of stress and strain. See, this modulus of elasticity is E is the so constant. It is E is constant for a given material. It is constant for a given material. It is constant for a given material, guys. Okay. So even if the stress is increased or strain is increased, so it will have no impact. So E is going to be constant for a given material. So that's why it remains constant. The ratio of stress and strain means E they are asking about, modulus of elasticity. So it remains constant. Option 2 is the correct one. Done. Sure. Next, so what is the Young's modulus of elasticity? See here. So let's suppose this is a wire which is of length L and its cross-sectional area A. Now you applied some load, force. So here this force can be also equals to weight, or which is also can be written as load. Okay. So you applied some force, so that there is some change in length delta L. There is some change in length delta L. So now, so we know that the modulus of elasticity, the Young's modulus of elasticity, in this particular case, the modulus of elasticity is called the Young's modulus of elasticity. So which is the stress by strain, stress upon strain. So what is stress here? Stress is force upon area by strain is the delta L by L. Yes. So from here, so I can write, so Young's modulus of elasticity is FL by A into delta L. So this is a formula for the Young's modulus of elasticity, guys. So again it will have the same units as of the modulus of elasticity or same units as of the stress, because L delta L units will cancel. Force upon area means again units are Newton per meter square. So the units are again Newton per meter square. So you can write the dimensional formula for this. You know the Newton dimensional formula, you know the meter square. So force and area dimensional formula you already know. Done. So very important here, sometimes this force, in place of force they might mention so the weight. So the weight will act as a force. So you can write weight here. And sometimes they may also mention load. So you can write so the load value also. Done. Very important. So from now you should remember this formula. So what is Young's modulus of elasticity? FL by A delta L. FL by A delta L. So from here, so if they asked you to find what is the delta L formula, so then FL by AY. The delta L is FL by AY, the change in length, FL by AY. Clear? Chalo. So let's take one question. So the question number 9. So a wire of length L, area of cross section A is hanging from a fixed support. So the length of the wire changes to L1 when mass M is suspended from its free end. So the expression for Young's modulus is, see here, this is a fixed end, let's suppose. So initially a wire of length L, so this is a wire which is of length L. So a cross sectional area A, let's suppose it's cross sectional area A. So now a hanging from a fixed support. So the length of the wire changes to L1. So now its wire length has become, so the total length L1 when mass M is suspended from it. So when mass M is suspended from it. So then the expression for Young's modulus is, so the Young's modulus formula, what is Young's modulus? FL by A into delta L. FL by A into delta L. So I can write here F is nothing but, so some mass is hanging, so that the weight, so the force is equals to here weight, which is equals to mg, which is equals to mg. Force is mg. So its original length is L by, so area, so let it be in terms of area only. In the options the area is area only, they did not mention the radius. If they mention the radius, you can write pi r square. Okay, so and then what is the change in length? Original length is L, final length is L1, so the change in length is L1 minus L. So check for this option, mg L by A into L minus L1 minus L. Option 4 is the correct one. Done? Clear? Chalo. So let's go for the next question. So the Young's modulus of a wire of length L and radius R is Y Newton per meter square. So if the length is reduced to L by 2 and radius R by 2, so the Young's modulus will be, see, the Young's modulus is constant for a given material. Is constant for a given material. So even if you change the dimensions, its Young's modulus will not change. So it will be Y only. Clear, everyone? Sure. So let's take this question. So what's the question says here? The given graph shows the extension L of a wire of length 1 meter suspended from the top of a rope at one end with a load W connected to the other end. Okay, so W versus the change in length is given. So if the cross sectional area of the wire is, so 10 to the power minus 6, calculate the Young's modulus. See, it's the simple direct formula based. So Y is equals to, so see here, oh, sorry, FL by A delta L. So directly substitute the formula. So the force, so how much force is applied, they said. So when 1 meter length, so at 1 meter length, so what is the corresponding weight? 20. So the force is nothing but weight here. So length is 1 meter. So cross sectional area they mentioned 10 to the power minus 6. And what is the change in length? So it is 1 into 10 to the power minus 4. The length into that particular 10 to the power minus 4. If you take 40 load, so then the length you should take 2, and then the change in length will be 2 into 10 to the power minus 4. Here they said when the length is 1 meter. When the length is 1 meter, the load applied is 20 newtons. Okay, and the change in length will be, so that length into 10 to the power minus 4 according to the question. So that's why it's 1 into 10 to the power minus 4. So 20 by 10 to the power minus 10. So here we get, so 20 into 10 to the power 10. So 20 into 10 to the power 10. Yes or no? So 2 into 10 to the power 11 it will be. So 10 to the power minus 10. So A into delta L, right? So calculate the Young's modulus only. Yes. So it's 20 into 1. So fine, we got it. So 20 into 10 to the power 10. So which is nothing but 2 into 10 to the power 11. So option 1. So Newton per meter square. Done? Clear? So if they mention the length 2 meters, you should take length 2 meters here and the load 40 here, and then so the change in length 2 into 10 to the power minus 4 here. Done? Na? Chalo, good. So let's take this question. So what's the question says here? Find the elongation of a steel bar of length 1 meter having cross sectional area this much and then subjected to load this much. So and then Young's modulus also given. See what we required actually. So the elongation, that means the change in the length we required. So we have got the formula FL by A into delta L. So from here I need delta L here. So which is FL by AY. FL by AY. So force they gave how much? 1.5 into 10 to the power 4. The original length they gave 1 meter by, so the cross sectional area 1.5, so it's centimeter square, which is nothing but 10 to the power minus 4. So the Young's modulus, which is 2 into 10 to the power 11. Okay, so then the delta L is equals to, so we can write this as 1.5 gets cancelled. So if we send it to upside, 1 by 2 means 0.5. 1 by 2 is 0.5. So here 10 to the power minus 7. So 10 to the power 7. If it goes up, 10 to the power minus 7 into 10 to the power minus 3. So which is nothing but 0.5 mm. 0.5 mm. Option 2 is the correct one. Done, everyone? Chal. So let's go for the next question. The Young's modulus of steel is twice that of the brass. So I am taking two wires here. One is steel, the other one is a brass. So the Young's modulus of steel is twice that of the brass. Let's suppose brass has Y Young's modulus. So then steel has 2Y. So two wires of same length. So they both have same length L. So same cross sectional area A. Fine. So then one of the steel and another of the block are suspended from the same roof. If you want the lower ends at the lower ends of the wires to be at the same level, see here, understand this statement. So if we want the lower ends of the wires to be at the same level, so that means the extension should be same in the both. So the delta L in this should be equals to delta L in this. Okay, so then weights added to the steel and brass must be, so simply, so the delta L of brass must be equals to the delta L of steel. This you should catch. So what is the delta L formula just now we wrote? So the delta L is FL by AY. So F of brass, L of brass by A of brass and then Y of brass. So which is equals to, so we can write here F of steel, length of steel by cross sectional area of the steel and then Young's modulus of the steel, right? So then I can write here, so see, so we need the weights of steel and brass must be in the ratio. So they both have the same length L gets cancelled, fine. So and they both have the same cross sectional area gets cancelled. So next, so we need weights added to steel and brass weights must be, so Fs by FB, so is equals to Ys by Yb. So here I can write, so the Fs by FB is equals to, what is steel? 2Y by brass Young's modulus Y. So Y gets cancelled. So the Fs is to Fb is equals to 2:1. So the Fs is to Fb is equals to 2:1. So this is a option 3 correct one. Done guys, everyone? Chalo. So let's go for the next question. The following 4 wires are made of the same material. Which of these will have the largest extension? So the delta L is more for when the same tension is applied. So same tension means same force. See again the same formula, delta L is equals to FL by AY. Right? So same tension is applied. So the F is same for everyone and then the length is different. So and then so same material, the Y is also same. So I can say the delta L is directly proportional to L by A. So I can write, so the delta L is directly proportional to F by, so here diameter is given. So let me write F into, so D by 2 whole square, the formula F into D by 2 whole square, because the radius square, actually radius means D by 2. So here pi is constant. So the delta L will be proportional to F 4F by, I can write, sorry, not F, L. So here it is L by pi into, so in place of radius I am writing d by 2 whole square. So 4 will go up, 4L by d square, because the pi is again constant. So the change in the elongation, the largest extension, it will depend on the length and d square. So that means the delta L is directly proportional to L by d square. So what you do is, for all the 4 options, you check the L by d square ratio. So here L you know, d square you know, so d value you know. Here L you know, d value you know, L you know, d value you know, L you know, d value you know. So for whichever the option, if you get L by d square value more, so that will have the more extension, maximum extension. Clear? So simply you have to substitute for option 1, for option 2, option 3, option 4. So what is delta L? So in whichever the case the delta L is more, so in that case the extension we can say the large. Clear guys? Understood? Chalo. So chalo, so that's it from my end for today's session. So very simple chapter. So it's a short lecture. In the next lecture, so we'll discuss about the remaining topics. So till then, keep studying. All the very best. Bye. Take care.